We're on example 5 from section 5.6 on the real zeros of a polynomial function. So in this example, we're defining the real zeros of this function, and we have a note here that this would be the same thing as if we were solving this equation. Remember, the solutions and the real zeros and the x-intercepts, all the same thing. So that's just a note to remind us that that's the same idea. So we start by determining the maximum real zeros. And what would that be? Well, it would be 4, right? Because that's the highest power on x, the degree of the polynomial. That's the most we can have. How many positives? We're going to count the sign changes in f of x. Positive to positive, no change. Positive to positive, positive to positive, positive, positive. So there are no sign changes. So we're not expecting any positive real zeros. We'll plug in negative f of x to find the function we need for counting negative real zeros. And recall that when we plug in a negative into an even power, it just stays positive, right? It becomes positive. So only the terms with an odd power on x are going to change sign. So 2x to the 4th is still positive, but 13x cubed now is negative. 29x squared is still positive, but the 27x is now negative, and of course our constant doesn't change. So count the sign changes to determine the negative real zeros. Positive to negative, there's 1. Negative to positive, 2. Positive to negative, 3. And negative to positive, 4. So 4, or it's possible that we have 2 non-reals, so then we would only have 2 negatives, or it's possible we have 4 non-reals, so we don't have any negatives. Recall it said the number of sign changes less an even integer. So I can take 2 away from 4 and I can take 2 away from 2. Every time I take 2 away, I'm saying, well, maybe we have a conjugate pair of non-reals as zeros. Okay, so I'm either looking for 4 or 2 or 0 negatives and no positives. All right, P is our constant, and the factors of 9 are plus or minus 1, plus or minus 3, and plus or minus 9. Q is the factors of our leading coefficient, plus or minus 1 and plus or minus 2. And P over Q will be our potential rational zeros. Well, we've just said there aren't any positives, so there's no point in listing positives here. But I do have negative 1, negative 3, negative 9, each one of these over this one, but only the negative because we don't have any positives. And then now over 2, negative 1/2, negative 3 halves, and negative 9 halves. Okay, so if it is a rational number, the zeros are rational, they're on this list. They have to be. Okay, let's start with negative 1. That's an easy one to start with. And our coefficients are 2, 13, 29, 27, and 9. Bring down the first number, multiply, add, multiply, add, multiply, add, multiply, add, and we did find a real zero, negative 1. And this is our new depressed equation, or the coefficients of our depressed equation. Now, something I did not mention before, but we need to be aware of. Remember from 5.1, sometimes we had, when we were looking at zeros, we had different multiplicities. We might have had x minus 3 to the 2nd power, right? So that 0 of 3, if it's x minus 3, the 0 is 3, raised to the 2nd power meant it had a multiplicity of 2. That means that if negative 1, for example, has a multiplicity of 2, I should be able to divide it into the depressed equation. So just because I found negative 1 doesn't cross it off the list, because it might occur again. So until I get a remainder that's not 0, I'm not sure, I haven't exhausted the number of times that negative 1 is a 0. So let's try negative 1 again, using the depressed equation here. 2, 11, 18, and 9. I don't want to use this because I've already done that, right? Bring down the first number. -2, 9, -9, 9, -9, 0. So indeed, -1 worked a second time. And now that leaves me with this depressed equation. Okay, and what is that? 2x squared plus 9x plus 9 equals 0. Now, how did I know it was x squared? Well, we started with x to the fourth, and when we divided, this would have been x cubed. Divided again, that's x squared. Or, after the remainders here, that's the constant, that's x to the first power, that's x to the second power. Okay, so I'm down to a trinomial. So I could take this trinomial and try to factor it, or put it in the quadratic formula. That's perfectly fine. -b plus or minus the square root of b squared over 4ac, and determine -b plus or minus the square root of b squared minus 4ac all over 2a. Sorry, I'm getting in a hurry. Okay, we have -1, we have -1. We could test -1 again in synthetic division, or I could just try to factor this. Let's see if we can factor this. Two integers that multiply to 3, and if I put 3's here, that would give me my 9. That gives me my 2x squared, but do I get 9x in the middle? 3 times 2 is 6, 3 times 1 is 3, so yes, that would FOIL to this. So 2x equals -3, and x equals -3 halves, and x equals -3, right? 2x plus 3 equals 0, 2x equals -3, x equals -3 halves, x equals -3. Now look what we found. We found -1, -1, -3 halves, -3. They're all in our list. And we found 4 negative real zeros. There are no non-reals. So the real zeros are -1 with a multiplicity of 2, it occurs twice, -3 halves, and -3, and they just occur once. Those are our 4. Okay, so the example 6 says to use the real zeros in the equation from example 5 to factor. The whole point of this is to be able to factor f of x. Okay, so what did we find? We found -1 is a 0. That means x plus 1 is a factor, and it occurs twice. We found -3 halves, so that means x plus 3 halves is a factor. It occurs once. And -3, so that means x plus 3 is a factor, and it occurs once. Now, we aren't quite done, because notice if I FOIL all this and multiply all this together, the first term has to be 2x to the fourth. I can see where I'd get an x squared here, and then multiply by this x to the first to get an x cubed, and then multiply by this x to the first and get an x fourth for this. But where do I get the 2? Well, that's that a that sits right there. So at the end, all you have to do is look back up here and say, what was a? There it is. If I don't put that there, this is not the same thing as what we started with, right? And now we can look at it, and this looks like a 5.1 problem, where you look at it and say, what are the zeros? Oh, x plus 1 equals 0, x is -1, multiplicity 2, x plus 3 halves equals 0, x equals -3 halves, x plus 3 equals 0, x equals -3. We can now see all the real zeros of this polynomial function.